What is going on, guys? Today we're going to be talking about some non-linear data structures. So the first one we're going to dive into is trees. Now, before I get into this, I want to say if you're enjoying the channel, if you like the content, please like and subscribe. If you want to get a job or internship in tech or big tech, check out the top link in the description. But with that being said, let's get right into trees. So are the tree data structures are basically built using tree nodes, a variation on the nodes you already created earlier in linked lists and before, and are another way of storing information. Specifically, trees are used for data that has a hierarchical structure, such as a family tree or a computer's file system. The tree data structure you're going to create is an excellent foundation for variations on trees, including AVO trees, red-black trees, and binary search trees. So binary search trees are a type of data structure with the added condition that the left node must be less than the parent node and the right node must be greater than the parent node. Each left and right subtree itself is a binary search tree, which makes searching for elements more efficient. So we'll look more into why that's efficient and how to create one in the future. Now, heaps are another variation of the tree data structure and are adept at keeping track of the maximum or minimum value held within, referred to as max heaps or min heaps, respectively. Specifically, heaps are a type of binary tree, since each child node is either greater than or less than its parent, depending on if it's a max heap or a min heap. They're efficient for accessing the root value, which will be either the max or the min. Again, depending on the type of heap and also inserting new values. Now, a min heap is basically when the root value of that tree is the smallest, and then a max heap is when the root value of that tree is the biggest, and it just keeps getting smaller. Whereas a min heap starts out small and then keeps getting bigger as you go down the tree. Now, the first thing we're going to be taking a look at here is the tree's introduction. So here's a little tree here. So trees are an essential data structure for storing hierarchical data with a directed flow. Similar to linked lists and graphs, trees are composed of nodes which hold data. The diagram represents nodes as rectangles and data as text. Nodes also store data to 0 or more other tree nodes. Data moves down from node to node. We depict those as lines drawn from the rectangles. Trees are often displayed with a single node at the top and connected nodes branching out. So let's say you have a computer, right? You're all computer science students. So if you look in the photos directory of your, let's say your computer or your Mac or whatever, you will probably see either Safari or Wedding. Let's say you have a Safari folder and you have a Wedding folder. Now the Safari folder is not like the Mac Safari, it's like the actual Safari. It's like the uh, the desert and the jungle, right? Like that type of terrain. Now, in the Safari folder, you'll most likely find a lion and a giraffe picture inside of that folder. And then inside of the wedding folder, you'll probably find vows and bride, right? That kind of makes sense. So this is the root node. This is the left child of the root. This is the right child of the root. And these are siblings. This is a parent, of course. And these are leaf nodes. And again, if this is the parents of these two, this is the parent of these two. And these two are siblings, these two are siblings, right? And these are all siblings as well. Okay? So family tree structure is also another example. Now trees grow downwards in computer science, and a root node is at the very top. The root of this tree is photos. Photos references two other nodes, Safari and Wedding. Safari and tree and Wedding are children or child nodes of photos. Conversely, Photos is a parent node because it has child nodes. Safari and Wedding share the same parent node, which makes them siblings. Note that the Safari node is child to Photos and parents to Lion and Giraffe. It's extremely common to have nodes act as both the parent and the child. When a node has no children, we refer to it as a leaf node. Okay, what are the four leaf nodes in the diagram? This one, this one, this one, this one. Which node has no parent, meaning nothing is above it? The photos, right? What is the sibling node to lion.jpg? It's going to be giraffe.jpg, and these could also be siblings. Now, tree varieties. So trees come in various shapes and sizes depending on the dataset model. Some are wide, with parents referencing many child nodes. Some are deep, with many parent-child relationships. Trees can be both deep and wide, but each node will have at most one parent, otherwise that wouldn't be a tree. So this cannot point to, let's say, this one. Sorry, this points to this one, right? So you cannot point it to another one, because otherwise that wouldn't be a tree, right? So each time we move down from a parent to a child, we're moving down a level. Depending on the orientation, we refer that to as a depth, counting levels from the root node, or height, counting levels up from a leaf node. Okay. Now we have a binary search tree. Now, binary search tree constraints are placed on a data or node arrangement to solve difficult problems like efficient search. A binary tree is a type of tree where each parent can have no more than two children, known as a left and right child. Now, to make it even more difficult, the binary search tree is where the left child must be less than the parent and the right child must be greater than the parent. These constraints of the binary search tree allows us to search the tree efficiently. At each node, we can discard half of the remaining possible values. Now, let's look at it this way, okay? So this is a binary search tree. Basically, you have this root, right, 39. Everything less to this, left to the of this is going to be smaller than 39, and everything to the right is going to be greater than 39. So let's say we were to find 69, okay? So is 69 greater than or less than 39? It's greater, right? So you move here, right? You move here. Now you can disregard all of this and just throw it away because you don't need all this. Then is 69 greater than or less than 70? It's less than, so we go here. And then is 69 greater than or less than 64? It's greater than, and here we go, we found it. Right, so it's cutting down the tree in half every single time, right? And that's going to be called log n. So trees are useful for modeling data that has a hierarchical relationship which moves in the direction from parent to child. No child node will have more than one parent. So recap some terms. The root is which has no parents, one per tree, right? Any tree can have one root. A parent is a node that references other nodes. A child is referenced by other nodes. A sibling which is nodes that have the same parents. Leaves are nodes that do not have any children. And levels or is the height or depth of the tree. So root nodes are at level 1, their children are at level 2, and so forth and so on. So let's take a look at the quiz here. Alright, 8 questions. Okay. Tree nodes that have no references to other nodes are known as leaf nodes because they're at the very bottom, right? Tree nodes which share a parent are called siblings. What would make a deep tree? Each node has at most 2 children, a philosophy class, many children at each level, many parent-child relationships. A tree node which holds references to other nodes is called a parent node. In a binary search tree, values in the left child are less than the parent, and the right child are greater than the parent. A tree node without a parent is called a root. What would make a wide tree? Many different data types and different nodes, many child nodes per parent node, many parent nodes per child node. Many child nodes per parent node, because then that would make it wide, right? And the last question, a tree node which is held as a reference by another tree node is called a child node, because trees are composed of nodes that reference other nodes, and the nodes being referenced are known as children or child nodes. Got 100, but yeah, thank you so much for watching, and I will see you in the next one.